But my name is Mark Kurtz. I direct the machine learning team at Neural Magic, where we focus on making deep learning more accessible and cheaper and more performant on deployments. If you'd like to connect or follow, I'm on LinkedIn and Twitter. Twitter, I just recently started, so I have very few followers. So anyone that wants to follow me, I'd love that. But let's go ahead and get started. So going through today's agenda, just generally going to talk through NLP optimization techniques. So whenever we're looking at these large transformer models, they can be expensive to deploy. They're very large and very compute intensive. So we'll talk through just some general optimization techniques for reducing that compute and reducing that that latency and throughput. We'll go through what happens whenever we combine the techniques, and then also talk through kind of what it looks like whenever we start trying to optimize our model. So when should we optimize? Does model size affect the optimization? Does sparsity hurt generalization? And then finally, we'll end it with a performance benchmarks and in a demo, and conclude with a Q&A. All right, so talking over NLP optimization techniques. So structured pruning. Structured pruning removes large sections of a network such that matrix shapes are removed. So you can think of kind of channels or layers. We're looking at whole matrices that we're removing from our weights and our activations. So looking at layers, we can look at BERT, where we go from a baseline 12 layer into kind of looking at the original TensorFlow and Google implementation. They had a medium BERT that was 8 layer and a mini that was 4 layer. This generally gets linear speed up since we're getting rid of whole layers at a time, including the attention and fully connected. And then we can talk about removing hidden dimensions. So hidden dimension size being our embedding size and what flows through the network. The baseline BERT has 768. And then again, in the original Google implementation, we have a medium that was 512 and a mini that was 256. This gives nonlinear speed up. Self-attention and also the fully connecteds within it scale with O(n) squared. So as we increase the hidden dimension size, the compute goes up a lot for these models. And then additionally, we can talk over removing individual attention heads. There's been quite a bit in research to talk over this, where the baseline is 16 attention heads. You can prune these away while training. Generally, it's limited speed up. That's been shown in research papers so far. Getting to 99% recovery of whatever the original was, you can usually get to around 20% speed up. And then just looking at what the effect of structured pruning has, absent of distillation, which we'll get to in a little bit, you can see how whenever we go from BERT tiny, BERT mini, small, medium to base, how our glue scores drop, right? So structured, removing a lot of the capacity of the network and it not able to retain that. Now let's talk over unstructured pruning. So this is where we take a dense neural network, and then we're going to remove individual connections, individual weights from that network. So we end up with a sparse version on the right. So we're going to mask individual weights in the network such that the matrix shapes remain the same, right? So our fully connected, our convolutional neural networks, whatever they are, our weight shapes and our activation shapes all remain the same, but we're going to add zeros into that. And then looking at NLP specifically, generally we're not going to prune the embeds, and this is because we don't get a lot of speed up whenever we do that, and additionally can affect the accuracy quite a bit. What we can target is attention matrices and fully connecteds within kind of the general transformer architecture. And then looking at full unstructured, so this is meaning that we put no restriction on which weights we want to mask out. We're just going to go by and weight by weight individually and mask them out to 0. This is supported by deep sparse on CPU inference. This is a free to use product out of the company I work for, Neural Magic, where we get speed up from these sparse networks. And generally, we can get about 1.5x speed up at 50% sparsity and 99% recovery. This is before distillation. So we'll go through what it looks like, how those numbers change after we add distillation in a little bit. And then finally, we can talk over semi-structured. So this is where we're going to mask in blocks. So we're going to look at blocks of 4, for example, take all of the weights in a fully connected matrix, and we're going to block them by 4 and then see how we prune out. So this is something that NVIDIA has with their Ampere GPUs, where if you look at subsequent blocks of 4, any 2 of those can be 0, and they'll be able to generate speed up from that. And usually this gets about 1.25x speed up for, actually I should say in the best case, 1.25x speed up for 50% sparsity and 99% recovery. And then let's jump into quantization. So this is where we take a larger FP32 precision, and then we're going to reduce it down to N8 or N4 or something like that, right? So you can see on the right, we have a distribution of FP32 weights. We want to compress these down into an N8 range. This gives us a reduction in data movement, as well as an increase in compute speed. And then dynamic versus static quantization. So it's a little bit of a difference. Dynamic means that as the activations are flowing through a neural network, we're going to calculate what the range is to how to scale that down into N8 on each inference, right? So what this means is that the activations aren't actually flowing through the network as N8. They go through as FP32 and they can convert it at compute time for each layer. Static means that we're going to go through and pre-compute the activations, the ranges on the activations, so that we just have essentially a statistical distribution representing these activations. And then that way we can actually have the weights flow through at N8 the entire time, because we're not actively measuring the distribution as it's flowing through the network. So static generally can be faster than dynamic. Downside is static usually you have to pre-train, or well, do a little bit of training to get it to converge. Dynamic, usually we don't have to train at all. And then talking about N8 versus less than N8, so N4 or things like that. N8, generally we can get full recovery across any domain, NLP included. It's usually pretty easy, limited hyperparameter tuning. The activations are generally always kept at N8, even if we go less than N4. If you see any of that research on N4, N2, or binary networks, usually activations are kept there. The weights can be compressed lower to save on model size. This is what a lot of the quantization research goes towards. But generally, they're complicated schemes that are required to go to less than N8. This means doing kind of piecewise bucketing of ranges and things like that, which makes it very hard to implement a speed up algorithm for it. So there's few inference implementations that run N8 for speed up. Looking at a few that do, engines, you'll generally get about 2.5x speed up for a BERT-like architecture. This includes deep sparse and ox runtime for CPU, and then TensorRT for GPUs. And then finally, looking at knowledge distillation. So on the right, you can kind of see what a knowledge distillation looks like. I'll go through the differences between these two in a second. But what we're going to do is train a smaller student model to mimic generally the outputs of a larger teacher model, right? We have a really large, accurate model. We want to distill its information down to a much more compressed model that's going to run faster. So let's walk through types of distillation. There's response knowledge, where we're looking at just the outputs on a network, right? So we have inputs going through a teacher and a student, and then we're going to compare the outputs from both networks at the very end and try and mimic, change our loss function so that's mimicking the teacher as much as possible. This is what Distilberg did in its research. We have feature-based, which rather than just looking at the outputs, it's also going to look at intermediate layers throughout the network, which is a little bit on what happens with this transformer distillation down here. We're going to look in between each layer and compare the outputs between those to try and get a better match throughout the entire network for the teacher to the student. And then finally, we have relation-based, which is actually looking at within the attention layers and things like that. It's actually looking at the mass that develop inside of there to try and actually mimic those mass from the teacher to the student. And TinyBERT, MiniLM, MobileBERT, all three of those implement both, actually all three, to try and get in their own way to try and get better performance. One note is that big note on this is that significantly helps both structured and unstructured pruned models. And looking at that 50% that we were talking about earlier, using distillation and a little bit of an update to with some better pruning algorithms, we can go from 50% unstructured all the way up to 90% unstructured in terms of sparsity. So we can get rid of 90% of the network and still recover to within 99% of the accuracy. So neural networks, very redundant. Then the next question comes in, can we combine techniques? So the answer is yes. This is actually one of the research papers that we have out right now that we've been actively working on. We call it OBERT, where we're going to remove more redundancies than any individual technique. And looking at the numbers on that, you can see our comparisons for different versions of OBERT that we created. This is just taking a 12-layer BERT model, pruning it. Well, first structured pruning, if we're doing a 6-layer or 3-layer. So removing either half the layers or 3/4 of the layers. And then we're going to add unstructured sparsity on top of that so we can get to a higher level. So you can see our speed up is going to beat out these pure structured techniques like TinyBird or DistillBird. And that's mainly just because we're combining and because structure leaves redundancy within the network. So now that we have a little bit of background on model optimization, a big question comes in on when should we actually apply the optimization, given that NLP pipelines can be a little bit complicated on training. One option is on fine tuning. So looking at BERT, we have a pre-trained NLP model that we're going to fine tune onto a data set first, and then we're going to start pruning. So for example, if you're working with a squad data set or something like that, we're going to train for about 2 epochs, and then we're going to begin pruning. And so converge on the NLP model, continue training and start pruning with distillation until we get convergence over several epochs. Several epochs can be actually pretty long. It can go from anywhere from for something that was originally 2 to 5 epochs, it can change it up to 10 to 30 epochs. So it can be a little bit longer to try and actually get convergence. And then looking at the results of doing this. So with unstructured, we can get to 99% recovery for 90% sparsity. This is on a BERT model with about 6x on the epochs, training epochs for larger data sets. The one issue with pruning on the downstream or fine tuning is that smaller data sets suffer. So if you have something small with only a few hundred examples, few thousand examples, usually pruning on the fine tuning isn't going to work well because it doesn't have enough information to generalize. And for structured, generally there's even a larger drop if we're doing this. So for example, if we take our pre-trained BERT model, remove a bunch of layers while we're fine tuning, we're removing a ton of information from that network in terms of how each layer communicates across the latent spaces, and it does not perform well. We're probably going to drop about 5 points in accuracy, at least on the glue baseline. And then quantization. Quantization we're training when we're looking at a static quantization representation. We can run this after convergence of the prune model. And generally, we always do this after convergence of the prune model just to keep from destabilizing it. Since generally we want to keep it FP32 while we're sparse. And then once we kind of have our solution, start quantizing so we don't disturb the solution from its local minimum. Another option is doing it during pre-training. So for example, on the mass language modeling task. BERT very famously introduced pre-training and then fine-tuning on the data sets. So we can take a pre-trained NLP model and then prune during that pre-training and then transfer it down to fine-tuning while we're fine-tuning. So we can converge an NLP model on a large text data set, continue training and start pruning with distillation over several epochs. Obviously, this can be expensive. We'll get through that in a little bit since we're on the upstream, but it does have quite a bit of advantages. And then additionally, once we have that prune model, now we have a sparse architecture that can be generalized. So what we'll do is whenever we're fine tuning, keep that mask that was developed on the mass language modeling test, for example, keep that intact and not change it. And while we're fine tuning. So looking at results, same thing. We get to 99% recovery for 90% sparsity. I'll go through a bunch of different models that this works on for both cases. But you'll notice that we only had to do about 1 to 2x the epochs to actually get it to converge as compared to our dense baseline. For structured, recovers much higher. And this is a default research. If you look at mini-LM, TinyBird, MobileBird, all those, they're all doing this approach as well. And then quantization, again, generally we just always recommend doing quantization on the downstream after you're done fine tuning. This is to avoid any instability in the training process as you're kicking off these models. So just kind of going through comparison and insights. Post-training, quantization works well with dynamic, and pruning does not work well for post-training currently. So this is just talking over, did we have to train at all, right? So looking at after we get, if we could just take our model off the shelf, just do one shot, don't worry about retraining at all, just try and prune it. Pruning doesn't work well at all. This is an active research topic for us right now. We're hoping to do better on it, but generally we require retraining. So this is kind of why we went down the pre-training and fine-tuning pathway. But quantization does work well with dynamic. And then looking through, generally pruning during pre-training is best. So it's more expensive, or it can be, but it's used across all of your fine-tuning data sets once you have a vocabulary that you want to converge on, and it generalizes better for smaller data sets. Oh, yeah. Yeah, this is generally abstract across any problem. Yeah. The examples that we have right now are across primarily encoding networks and looking at text classification, token classification, document classification, question answering. The generation side is something that there's more active research around, but has been shown to work. It just doesn't work as well currently. That's an active research area for us right now. But yeah, great question. And then the other thing to say is that, so one of our other products that we have open source is the sparse, and it has pre-trained and pre-sparsified models ready to use. So you can just pull one of those down. We'll go through a demo at the end. Just being able to pull it down and then use it on your data set. And then finally, looking through pruning during fine tuning. Generally, you want to use this if pre-training isn't available. So the original model that you're using isn't available, or the training process or the data set isn't available, or pre-training is too expensive, then generally try out pruning during fine tuning. And finally, quantization, as I said before, generally always apply this after fine tuning on the data set, or if you want to do dynamic, then you can apply it as one shot after you have your trained model. So another question that comes in is, how general, kind of to that point, not necessarily on across domains or subdomains, but also across model sizes and different types of models. So how much does optimization affect accuracy, model size after effect optimization? So number of layers has limited effect. Distillbert, BERT-based, we've done both of these. They recovered to 99% at 90% sparsity, generally work very well. And the kind of thought behind that is that depth scaling seems to add the same redundancies in the neural networks, right? So you kind of have a choke point at the beginning of the network where you have only so much information that can go through and you're going to keep trying to extract it. That means that all the layers after can generally be pruned to essentially the same level of sparsity. Width and the hidden dimension can affect it though. So BERT large recovers to above 99% at 9% sparsity, which has a higher hidden dimension size. And TinyBERT, which is early research for us, but we usually get to 99% at 70 to 80%. TinyBERT has a smaller hidden dimension size. This is generally just because as we reduce the hidden dimension sizes, we're compressing the model a little bit more and removing some of the redundancies. And then this also gets complicated whenever we're combining it with complicated distillation schemes, but generally you can get to 70, 80, 90% sparsity. A lot of these networks can essentially be completely removed and the model still function almost exactly the same. And then looking at the effect of the optimization, model size and optimization on performance. So number of layers doesn't really matter, as we talked about before. It's just linear scaling, and since we get the same recovery for the same sparsity, we're going to get the same speed up. So Distillbert and BERT-based, we both of them get about 4.75x speed up on deep sparse CPU. This was at batch size 1, sequence length 128 for one of our block sparse quantized models. And this is mainly just because depth scaling is adding the same compute versus memory ratios. So we're not going to get a lot of benefit from that. Width and hidden dimension size does help out quite a bit though. BERT large gets a 6.75x speed up for the exact same setup. And this is because it has a lot more compute because it has a higher hidden dimension size, or a larger hidden dimension size. And then just generally BERT large is probably the best use case for TensorRT. TensorRT has some problems with smaller networks in terms of being able to get speed up for sparsity, but for BERT large, they can get to 25% speed up. And that's for that 2-4 block pattern, so 50% sparsity listed earlier. Another question is just generally does sparsity hurt generalization, right? So we're removing a lot of information from the network. And because of that, it might limit the flexibility of the network, right? Since we've removed a lot of weights, it might not be able to fine tune to new data or unseen data or even new domains. And contrary to this, a lot of our research, pretty much all of our research, has shown it can generalize in some cases even better than dense. So there's a few papers that we have out. One is how well does sparse ImageNet models transfer on the computer vision side. A lot of interesting results in there, which is that actually the sparse models did not overfit to training data. So if you did random labels, for example, the common experiment of randomizing the labels with the training data and neural networks just being able to memorize that pattern again, the sparse networks actually were not able to memorize that. So showing that, I'll get to in a second, but showing that sparse is acting as a regularizer to keep generalization in the network. And then additionally, our optimal BERT surgeon that I linked to earlier, this paper also goes through a little bit on sparse transfer and the applicability there. So as I said, sparsity acts as a regularizer to limit the overparameterized neural networks from overfitting to the data. So all of these neurons and weights that we're removing were just there to essentially memorize training data. So think especially with these large NLP models, how they would start memorizing credit card numbers. Sparsity is a way to try and prevent that. We haven't checked out the credit card number thing exactly yet, but at least on the computer vision side, we've seen this quite a bit, where it gets rid of this overfitting and this memorization of the data. And then talking over some new results that we haven't published yet, but that have been interesting for us actually over the past month to 2 months. Looking at out of domain on the PubMed data set. So this is BioBERT. We can look at BERT-based case. So this means just taking the English text model and fine-tuning it on PubMed data. So looking at PubMed being medical and bio data. It gets to 80.9 average across a lot of different data sets. This is a lot of NER applications and some document classification and things like that. It gets to 80.9. BioBERT, where they took that English text corpus and then reran MLM, mass language modeling, on the PubMed data, got to 83.4 average across all data sets. And then comparing our sparse versions, sparse BERT-based case got to 80.7, almost exactly on the BERT-based case. And then doing the exact same thing where we took that sparse model and ran mass language modeling onto the PubMed data set, we got to 83.3, so almost exactly matching the BioBERT. All right, so again, this is something that's completely out of domain in general for what this model was originally trained on, but it still is able to work with that data. And then something that's really interesting that is really preliminary results, but I wanted to share, looking at zero shot. So this is something that we've been looking into, especially for information retrieval. We're looking at deploying a model and using that essentially within a database to be able to deploy a BERT model, use it in a database so you can get semantic relevance between your text index lookup. So looking at the NQ dataset for the top 20 retrieval accuracy, BERT-based uncase gets to 1.75% accuracy on it, and the sparse BERT actually got to 6.7. So being able to just do a zero shot implementation, just kind of showing that these sparse models are generalizing a little bit better than their dense use cases. All right. And then let's go ahead and jump into a little bit on performance. So this is looking at all that research that I just went through, actually getting some numbers on what this means to the end user once you go to deploy. So this is looking at CPUs versus GPUs, and taking our 80% 12-layer sparse quantized BERT and comparing it to a dense BERT on GPUs. So an 8-core CPU is able to beat both the V100 and the T4 GPU in latency, and even a 4-core CPU Intel MacBook. I don't think mine can run it, right, Michael? but taking one of the newer ones that has VNI on it is actually able to beat a T4 GPU, right? Your MacBook can beat a T4 GPU on BERT. And then diving in a little bit, kind of going through those performance numbers I was talking about earlier on BERT large, BERT base, and distill BERT. This kind of puts everything into perspective, where you can look at the throughput at batch size 32. Here's BERT large baseline, and 80% sparse quantize, exact 99% recovery is able to significantly improve that throughput all the way up to almost 200 items per second, to the point that it's actually over 2x the BERT base, even though BERT large has significantly more compute in it. BERT base, after optimizing, is able to get all the way up to 603.7. And then distill BERT, just realized I had a incorrect label there. This should be distill BERT, but it's able to get almost to 1,000 items per second. Again, at the same setup. All right, so let's go and dive into a benchmarking demo just to show all of this working. Yeah. That's a great question. We do train the sparse one a little bit longer, actually 8 epochs compared to 5 epochs generally. And this is because we see the dense one actually usually max out around 2 epochs, and we continued on just to make sure that it's within the range of error. So usually 5 epochs cuts that off. The sparse models take a little bit longer to converge, but by 8 epochs, those are generally within the margin of error. But yeah, great question. That's a good question as well. Currently, there isn't a setup for sparse training yet that can support it, but it is something that we're actively looking into to see if we can speed that up.
We have audience questions. This has a mic in.
Oh, yeah.
Yeah, it'd be good to repeat the question too. So
Oh, yeah, great point. So real fast, the question was on second one was whether or not the training process was faster for the sparse models. Currently, it is not because there isn't a system, at least a production system, that supports sparse training. This is something that we're actively looking into to see if we can speed up. And then the first question was asking for the sparse. Let me go back to this. For these models, were they trained for the exact same amount of time on the downstream task? And the answer was the 5 epoch. For the dense base cases, those are trained for about 5 epochs. That's generally where we see convergence and just kind of oscillating around the validation error. And then the sparse ones take a little bit longer to converge. And we train those usually for about 8 epochs. And that's where, again, we see bouncing around the validation error. All right, perfect. All right, and then jumping into a demo. So just to show what this performance looks like. So I have a server spun up. Let me clear all of that out. I have a server spun up. This is a 24-core CPU, so it's going to be quite a bit more power than what my MacBook can do, and what the laptop numbers were. But we can kick this off. This is going to run a BERT base model first, so just the dense model use case. So what it's going to do is it's going to spin up the deep sparse engine. It's going to run a bunch of sample inferences through it, and then record the time. So we'll share all this out in case anybody wants to try it afterwards. But yeah, so it's kicking off now. It's going to go through 10 seconds for benchmarking, and then we'll see the output for performance on that. All right, so we got to 84.5 items per second. And now if we take this benchmark, which you'll see we have these things called models. Actually, let me paste it in here because it's going to take a little bit. So let's kick that off. But what you'll see is that I'm just giving it a different what we call zoo stub. And this is just how we identify the models in the sparse zoo. It's going to download that model and then run it automatically. So it's spinning that up. This is a 12-layer, 80% prune model that's also quantized, gets to the same baseline as a dense model, or within 99% of that dense model. And you'll see that we were able to get to 597 items per second, right? So a significant speed up over that unoptimized model. Great. And then I'm not going to go through the training demo in here because that would take a little bit of time. I don't think anybody wants to sit here and watch a weights and biases chart. But I know some people like to. But we'll go through just kind of two separate tasks, or two separate resources that we have. One are what we call try it now pages, which are on the Neural Magic website. This will actually walk you through how to go about using our sparse models and transfer learning them onto your use case and be able to use them. The thing that I want to call out is the sparseml.transformers question answering. So all you need to do is pip install sparseml, and then it installs the CLI commands that you can begin using. We have creating the teacher for distillation, and then also how to kick off the transfer learning. So underneath the hood, what these are doing are they're taking the sparse weights and pulling those down, instantiating them actually into a Hugging Face pipeline. And then we've also added what we call our modifiers onto the top of it, which load recipes. And recipes I'll show real fast if I can find one. But recipes are just the way that we encode our hyperparameters for, oh, this is the wrong one, so I apologize. Recipes are how we encode the hyperparameters behind pruning and quantization. There can be quite a bit, there can be a little bit of complexity to it. And overall, we don't want to have just kind of an overload of hyperparams going through the command line. So recipes allow us to be able to encode everything into an easier to track system that essentially this just loads. It'll take over your training pipeline through sparse ML, and that way you can add any kind of modifier you want, including quantization, pruning, structured pruning, things like that. Just going through a recipe real fast. I don't know if that might be too small, but what's happening here is that we're just defining the number of epochs that we're going to run for, and they're just kind of general arguments up here you can play with if you'd like, but it'll run for this many epochs. We'll control the learning rate with these. We'll start distillation with this, and then we'll do pruning with this one, and then finally quantization. And it runs like this. So we're working on documentation just to write up how to go about creating all of these, and how you can go about creating your own for your own models. But ideally, this is just kind of a simple system that you can use. And in the future, we're looking at building out a UI to make all of this interactive and automated. And yeah, I think that was about it. Just to go through kind of future work. Stay tuned, connect with either the company or with me. We got a lot more that we're working on, including more deep learning models, more use cases. I know document classification was mentioned earlier, so we're working on getting some sample models spun up for that currently, and then working on better distillation compression methods, working with those models like mini LM, things like that. One-shot optimization research, and I don't know why that is stuck in there, but one-shot optimization research, and then additionally working on the use cases I was mentioning earlier, like information retrieval, and then getting into NLG with summarization, translation. And then on the computer vision side, we have segmentation and actually an upgrade to our ops detection pipelines. So we're on YOLO v5 currently, looking at getting the new upgrade for the YOLO v6 models. And yeah, let us know if there are any use cases or models you'd like to see us work on. But that's everything I had. And yeah, happy to open it up for discussion and Q&A.
See if there are any. Thank you. Let's see if this works. Okay, I will give you this thing so that you can ask your question in the audience here. And then people who are attending remotely, if you use the raise hand feature, then in turn, I will enable you to ask your question, or you can enter your question with the Zoom Q&A feature.
So you mentioned the 90% sparsity figure a couple times.
Yeah.
I'm curious on how that's measured. Is that the number of parameters that you've reduced, or is that the size in memory, or is that measured a different way?
That's a great question. So what we're looking at is just kind of set the stage. Are the fully connected in the intention layer? So all the matrices that we are targeting pruning, then we're going to mask out 90% of those weights. So 90% of them, we're just going to put zeros over them, and keep only 10% remaining as non-zeros. The embed, this is leaving out the embeds that we don't touch at all. We'll quantize those, but we're not going to go ahead and prune those. We don't get speed up from those, and they're pretty sensitive to accuracy. But yeah, if you're looking at a fully connected layer, we're going to go through and remove 90% of the connections, and only 10% of those are remaining then.
Okay, thank you.
Yep.
Questions in here? Don't have anyone on Zoom.
It's like a semi-question.
Okay. Hi. So have you tried this with other things besides like BERT or other types of models like I don't know, GPT or whatever the new one is? Yeah.
Yes, that's a great question. So we've been very focused on BERT, Stillbert, BERT large, things like that. We've done a little bit of preliminary research on GPT-2, and the beginning part of it was that we were able to get to about 80% sparsity, and to a human, it looked pretty similar, but the loss function actually went a little bit up in terms of what we would like. So this is an active research area that we're looking at to see if we can improve that further. But yeah, that was kind of the initial research that we had on more generative based models. We are also actively working on T5 right now to try and get that release. It's going pretty well, and we haven't seen any issues so far with that one. But that would mainly, and then we had a little bit of research on TinyBERT, which showed kind of 70-80% sparsity was reasonable for that model. But yeah, outside of those have been kind of our main use cases. We are looking right now for information retrieval on the bioencoder setup. and actively pruning those. That's been working out pretty well. And so hope to have that done in, the probably next month, 2 months maybe. And other than that, on the computer vision side, quite a bit there in terms of image classification, object detection, and segmentation models. So like YOLO, YOLACT, ResNet, things like that. Yeah. Oh. Yeah, definitely. So yeah, question from Natalia. Do you use next sentence prediction in these models or just the MLM? So actually, interesting enough, we found that just MLM for the upstream whenever we were pruning, at least for BERT and in these types of models, was fine to actually be able to get recovery. We didn't have to do next sentence prediction or anything like that. So it worked out pretty well. We didn't see any difference actually whenever we were comparing MLM alone or MLM plus next sentence prediction. And so given that it had an extra compute cost and took training, made training a little bit longer, we just got rid of that and it worked out pretty well in terms of recovery. But yeah, great question.
Related to performance.
Yep.
That you report.
No.
So the numbers that you report, how consistent are they? Like, did you run this over multiple times and report the average, or is this just like one static view?
Yeah, it's a great question. So in general, our philosophy is to do at least 3 training runs and do the average across those. Some of the more experimental stuff, like I was presenting as just the experimental results, that's been only like 1 run, things like that. But BERT, still BERT large, those are all generally averaged across 3 runs.
Gotcha.
Yeah.
Have you considered making Pareto curves? So instead of just showing it at a fixed number of, like you're doing a good job of trying to keep everything fixed in a fair apples to apples comparison, but you can see a bigger picture if you actually show the full trajectory.
Yeah.
Have you done any of those?
So funny enough, we have a little bit towards, let me see if I can dig it up, but we did have some more complicated graphs to kind of go along that line, and got some feedback they were too complicated in terms of getting them, but we're looking at, let me see if this is but yeah, let me see, which one is it? I think it might be this one. It's not that one, but we have been, maybe it's this one. We have looked at that. There's kind of 2 issues. Oh yeah, here we go. So we have graphs like this that we've generated, which this is older research, so this is less recovery and less speed up than what we have now. Quite a bit less actually. We were generating these, we got a little bit of feedback. They were a little bit more complicated than what they need to be, and also just the amount of compute that goes into generating these graphs and showing that curve is quite a bit. So what we've seen is just kind of deciding on 90% and then the 80% block 4 that we need for deep sparse VNI. That's generally a good baseline so that we don't have to spend a ton of compute and we don't complicate the readings. But if you want, actually, let me pull up. Do we have it in there? I think we do. Sorry, we just made an update to the Obert paper today because we have to go silent on it after today for submission. But so it hasn't gone live yet, but I think the old version might have a better comparison for what you're looking for in terms of pruning versus accuracy. Yeah, so at the top there.
Okay, cool.
There we go. But yeah, you can see the blue is our research. So significantly improves over the baseline. The green was something called movement pruning, which was out of Hugging Face. It used first order information. Well, I guess it just kind of walk through these real fast.
What's the x-axis?
The x-axis is going to be our sparsity. Sorry, yeah, let me scroll down a little bit. Yeah, so sparsity versus our F1 score on squad. So looking at these lottery ticket and sparse BERT, these were doing pruning on the upstream without distillation and then fine tuning. You can see they get to pretty poor performance and it drops off pretty fast. Movement pruning, this was just using magnitude pruning, which is a 0th order method. The green was movement pruning, which is out of Hugging Face, which used a first order method. They multiplied the weights by the gradients. And essentially what this was saying was that any weights moving away from 0 were good weights to keep. Any weights moving towards 0 were ones that you wanted to prune away. And they got to pretty good results with it. The blue is our research where we actually did both improvements to the 0th order, as well as introducing a 2nd order algorithm where we look at an estimated approximation of the Hessian as for each weight, its effect on the loss. And you can see that we're able to significantly improve over the baseline using both that and some better hyperparameters.
Cool. I don't want to take up too much time, but since we're already on this graph, what constitutes a dot? Like it looks like something has converged in order to make a dot here, right?
This was, yeah, it's a good question. That was just what the models were, the sparsity level was set at. So for example, this blue line, we had a 70, 80, 90, and 97% model that we created. The green line was 70, 80, 90, and 97% models.
Yeah,
and so on.
yeah, I get that. I just thought that, like, for example, the 70% that you're making an architecture such that it has 70% of the weight or whatever, 30% of the weights, but like you're still running that until some metric of conversion. Yeah.
Oh, yeah. So these were all generally run. These were run with the same number of epochs. I believe the blue line, we did 30 epochs, I think. So 2 epochs starting off for general convergence on fine tuning. I think, what did we do? I think it was 18 epochs of pruning and then 10 epochs afterwards to fine tune. And that's generally where we got to. Movement pruning, well, that was for the GMP route, the 0th order. The 2nd order that I was talking about, we did 10 epochs, so 2 epochs of fine tuning. And then I think 5 epochs of pruning and then 3 epochs of fine tuning afterwards. It's been a little bit since I looked at the numbers, but yeah, and the movement pruning ones are all 10 epoch training runs.
Okay. All right. Thanks.
Oh, yep. All right, and yeah, so from Natalia, how does reducing the max sequence length to 128 from 512 affect the model accuracy? Yes, that's a great question. Well, I was going to go back to my presentation, but I don't think I have anything in there on that. Generally, it's going to be application specific. So we haven't looked too much more into this. It's going to really depend on your data set. A lot of the glue tasks are fine at 128, and we haven't tried to go lower than that to see if there is an effect on that. And then for a question answering squad, 384 is a general baseline. Going less than that to 128 drops a few points in accuracy off of it. But the other thing I call out is that at least for document classification, one of the really popular ways is instead of processing the entire document, take the first 512 tokens or so, and just run that through as kind of a cheap baseline. And that generally works pretty well. So honestly, it's data set to data set dependent for how much sequence length is going to affect accuracy.
All right, let me pitch once again. Anyone on Zoom who would like to ask a question, you can put it in Q&A now or use raise hand, and I will enable you to ask your question live. And then let's see if there are any other questions from the live audience. Takers? Not seeing anything here. I'm not seeing anything here. So we'll wrap up Mark's talk then. Thank you very much, Mark, from Mark Kurtz from Neural Magic. And thank you to everyone who has been attending online. So I will pitch once again that we'll continue to try to do these programs fairly frequently. And if you'd like to give a talk, then you can send me a note. You should be seeing my email address now. And once again, the recording of this program this evening will be posted to the NLP XING YouTube channel. And you could subscribe to that channel to get notifications when we do post future videos.